explore how advanced metallurgy, precision rolling, and automated forming technologies transform raw steel into high-performance pipes and industrial components. The manufacturing process of pre-stressed wedges starts with hot forging, where heated billets are pressed into wedge-shaped dies to form the basic geometry. After forging, the wedges are trimmed and machined to achieve precise taper angles and accurate dimensions. CNC machines are used to cut the gripping teeth and refine the outer surfaces. The wedges then undergo heat treatment to enhance hardness and wear resistance. Finally, surface finishing, dimensional inspection, and functional testing are carried out before the wedges are assembled and prepared for delivery. The three-roll bending machine is designed to progressively deform flat steel plates into curved geometries, including conical shapes, through controlled rolling and precise adjustment of the rollers. Unlike cylindrical rolling, conical rolling requires asymmetric deformation, which is achieved by independently positioning and inclining the machine's rolls. At the beginning of the process, the flat steel plate is positioned between the three rolls. The upper roll primarily applies downward pressure, while the two lower rolls support and feed the plate forward. To prepare for conical bending, one of the lower rolls is set at a different height or angle compared to the other. This offset causes one side of the plate to experience a greater bending radius than the opposite side, which is essential for forming a cone rather than a uniform cylinder. Once the plate is aligned, the machine begins rotating the rolls. As the plate is fed through, the upper roll gradually presses the material downward. Because of the asymmetrical roll configuration, the steel plate bends more tightly on one edge and more gently on the other. This controlled difference in curvature forces the plate to take on a tapered shape as it passes repeatedly through the rolling zone. The operator closely monitors the rolling process, adjusting roll positions incrementally to refine the cone angle and ensure smooth material flow. The rolling operation is performed in several passes rather than a single heavy deformation. Each pass increases the curvature slightly, reducing internal stress in the steel and improving dimensional accuracy. The machine's robust frame and precise hydraulic controls ensure consistent pressure distribution, allowing thick steel plates to be bent without surface defects or loss of alignment. After the desired conical shape is achieved, the plate is removed from the machine. At this stage, the cone remains open along the longitudinal seam. A skilled worker then aligns the two edges carefully, ensuring that the cone geometry is maintained and that the seam fits tightly along its entire length. Following alignment, the seam is fully welded along its length. Welding permanently joins the two ends of the steel plate, transforming the rolled plate into a rigid conical structure. Care is taken during welding to control heat input, minimizing deformation and preserving the cone's dimensions. Once welding is completed, the cone is returned to the three-roll bending machine for final rolling. This post-weld rolling step is critical, as it helps correct any minor distortions caused by welding and ensures that the cone has a uniform curvature and smooth surface. The rolls apply gentle, even pressure around the circumference, improving roundness and structural consistency. Through this sequence of asymmetric rolling, controlled adjustment, welding, and final reshaping, that demonstrates its capability to produce high-precision conical components. The process combines mechanical accuracy with operator expertise, making the three-roll bending machine an essential solution for manufacturing conical steel parts used in industrial, structural, and heavy fabrication applications. The W1220X2200 4-roll plate bending machine is a robust mechanical device designed for the precise forming of metal sheets with both constant and variable curvature. It is widely used in metal fabrication industries, where steel plates of a specified thickness must be bent into cylindrical, curved, rectangular, or other complex shapes with high dimensional accuracy. This machine operates on a 4-roll configuration consisting of 1 upper roll, 1 lower roll, and 2 side rolls. The lower roll provides firm support to the metal plate, while the upper roll applies downward pressure to initiate bending. The 2 side rolls move independently to control the curvature and guide the material during the rolling process. This arrangement allows the machine to perform pre-bending, rolling, and final forming in a single setup, significantly reducing handling time and improving productivity. One of the key advantages of the W1220X2200 is its ability to handle both uniform cylindrical bending and variable radius forming. By adjusting the position and pressure of the side rolls, operators can produce cones, arcs, and non-standard profiles that are difficult to achieve with conventional 3-roll machines. This flexibility makes the machine suitable for applications such as pressure vessels, tanks, structural components, and heavy machinery parts. The mechanical drive system ensures stable operation and consistent rolling force throughout the bending process. The rigid frame structure enhances overall strength and minimizes deformation under heavy loads, ensuring reliable performance even when processing thick metal plates. In addition, the 4-roll design improves plate alignment, reduces slippage, and provides better control over the bending accuracy. Overall, the W1220X2200 4-roll plate bending machine is an efficient and versatile solution for industrial plate forming. Its capability to produce a wide range of shapes, combined with high precision and operational stability, makes it an essential piece of equipment in modern metalworking and fabrication workshops. The welding process starts with tack welding, which serves as the foundation for all subsequent welds. After the steel components have been positioned into the required curved configuration, the welder applies small tack welds along the joints. These welds are placed at carefully selected intervals to hold the plates and profiles in position. In curved beams, maintaining the correct geometry is especially critical, as the curved shape can easily be altered by thermal movement. Tack welds prevent the components from shifting or opening during full welding, ensuring that the curvature remains consistent. Although small in size, these tack welds must be strong enough to withstand thermal stresses generated later in the process. Once the structure is securely held by tack welds, the welder proceeds to the main welding operations. Manual arc welding techniques are commonly used for this type of structural work. allowing the welder to adapt continuously to the beam's curved geometry. The first full welds applied are typically root passes. These root welds penetrate deeply into the joint, fusing the steel components at their base. Achieving proper penetration at this stage is essential, as the root pass determines the overall strength and integrity of the joint. The welder controls arc length, travel speed, and electrode angle carefully to ensure a stable weld pool and consistent fusion. After completing the root passes, the welding process continues with successive filler passes. Because curved beams are made from thick steel sections, a single pass is insufficient to fill the joint fully. The welder therefore deposits multiple layers of weld metal, gradually building up the joint thickness. Each pass must fuse smoothly with the previous layer, as well as with the base metal. In curved sections, the welder adjusts hand movement and electrode manipulation continuously to follow the curvature. This prevents defects such as lack of fusion, undercutting, or uneven bead formation along the bend. Heat control is a critical aspect throughout the welding process. Excessive heat can cause distortion, altering the beam's curvature or introducing internal stresses, while insufficient heat can lead to weak welds. To manage this, welders carefully regulate current settings and welding speed. They also use controlled welding sequences rather than welding continuously in one direction. By dividing the beam into sections and welding them in a planned order, heat is distributed more evenly. This approach reduces the risk of warping and helps maintain dimensional accuracy. A common technique observed during the welding of curved beams is alternating welds on opposite sides of the structure. Instead of completing all welds on one side first, the welder applies several passes on one side and then moves to the opposite side. This balanced approach counteracts shrinkage forces caused by cooling weld metal. For curved beams, where symmetry is vital, this method helps preserve the intended arc and prevents twisting or lateral deformation. As welding progresses, special attention is given to joints where the web meets the flanges. These intersections experience significant stresses when the beam is in service. To ensure strength and durability, welders apply carefully controlled weld beads at these locations. Slight weaving motions are often used to ensure complete coverage of the joint area. Each weld pass overlaps slightly with the previous one, creating a continuous and uniform weld profile. The welder's experience is essential here, as maintaining consistent bead shape over long, curved joints requires steady control and concentration. In certain sections of the beam, reinforcement welds are added to increase joint strength. These additional passes provide extra weld metal at points expected to experience higher loads or stress concentrations. Curved beams are often used in architectural or structural applications, where forces are distributed unevenly, making reinforcement essential. The welder carefully integrates these reinforcement passes into the existing weld structure to ensure smooth transitions and strong bonding. Throughout the welding operation, pauses are taken between sequences to allow partial cooling of the steel. Controlled cooling reduces the accumulation of heat and further minimizes distortion. After cooling, the welder resumes welding adjacent sections, gradually advancing along the entire length of the beam. This step-by-step progression ensures that the beam remains stable and that weld quality is consistent from start to finish. Visual inspection is an integral part of the manual welding process, even while welding is still ongoing. Welders continuously assess bead appearance, penetration consistency, and joint alignment. If any section appears insufficiently filled or uneven, additional weld passes are applied immediately. This on-the-spot correction is a key advantage of manual welding, as it allows welders to respond directly to variations in joint fit or welding conditions. One of the defining characteristics of manual welding and curved beam fabrication is adaptability. Unlike automated systems that follow predefined paths, manual welding relies on the welder's ability to adjust technique in real time. The welder frequently changes body position, electrode orientation, and travel direction to maintain proper weld quality along the curve. This flexibility is particularly important when working on large beams, where access angles and joint orientations vary continuously. As the welding nears completion, the welder ensures that all seams are fully welded along their entire length. Overlaps between weld passes are carefully managed to eliminate weak points or discontinuities. The final weld structure consists of multiple integrated layers that act together to form a strong, unified joint. At this stage, the curved beam has transitioned from a temporarily fixed assembly into a solid structural element. The manual welding process demonstrated in the video highlights the importance of sequencing, heat management, and craftsmanship. Each weld pass contributes not only to joint strength, but also to the overall geometry of the beam. By carefully planning weld order, alternating sides, and controlling heat input, welders are able to produce a curved beam that meets structural requirements while maintaining precise shape. In conclusion, the manual welding of curved steel beams is a complex and labor-intensive process that begins with tack welding for temporary stabilization and continues through root passes, filler layers, reinforcement welds, and balanced welding sequences. Every stage depends on the welder's skill, experience, and attention to detail. The ability to adapt to curved geometry, manage thermal effects, and maintain consistent weld quality is essential. Through careful execution of each welding step, individual steel components are transformed into a single, robust curved beam capable of performing reliably in demanding structural applications. This process underscores the enduring value of manual welding expertise in modern steel fabrication. The production process begins with the thorough preparation of shuttering profiles. These profiles are cleaned using a fully automatic shuttering cleaner, which removes residual concrete and contaminants from previous cycles. Immediately after cleaning, a separating agent is applied uniformly to the profiles. This automated application ensures consistent surface quality and prevents concrete adhesion during later demolding, while also reducing manual labor and cycle time. In parallel, the steel pallets used as casting beds undergo a fully automatic cleaning process. Each pallet is cleaned to remove dust, hardened residues, and any remaining separating agent from earlier production. Cleaning and the application of a new separating agent are combined into one continuous, fully automatic operation. This guarantees a smooth pallet surface and provides optimal conditions for precise concrete casting and easy release of finished elements. Once the pallets are prepared, the system proceeds with plotting the contours of the elements. This step is fully automatic and CAD/CAM controlled. Based on digital production data, the exact geometry of floor slabs or wall shells is transferred onto the pallet surface. The plotted contours define the final dimensions, openings, recesses, and edge details with high accuracy, ensuring repeatability and dimensional consistency across all produced elements. Following contour plotting, shuttering profiles and inserted parts are positioned on the pallet. High-speed automated positioning systems place these components with absolute precision. Inserts, such as window frames, door frames, conduits, and lifting anchors are accurately located according to the digital model. The high positioning speed supports continuous production flow while maintaining strict tolerance requirements. For components that cannot be placed automatically, a dedicated workplace system allows for manual positioning of supplementary parts. Operators install special inserts or customized elements while following digital guidelines displayed at the workstation. After shuttering and inserts are completed, pallets are transported transversely by frequency-controlled cross-lifting cars. Reinforcement preparation and placement follow next. Reinforcement cages and meshes are assembled and placed using robotic technology. Robots position the reinforcement according to predefined layouts, ensuring correct concrete cover and structural performance. Once robotic placement is completed, manual finishing of reinforcement takes place. Skilled personnel adjust bars if required and perform quality control checks. This step verifies correct positioning, spacing, and compliance with design specifications before concreting begins. Any deviations are corrected immediately to prevent defects in the finished elements. Once the reinforcement is approved, the pallet moves to the automated concreting station. Fresh concrete is distributed evenly over the prepared pallet. The pouring process is precisely controlled to ensure uniform filling of all cavities formed by the shuttering profiles and inserts. Immediately after pouring, the concrete is compacted. Vibrating and smoothing systems remove trapped air, increase density, and create a smooth, even surface. This guarantees that the concrete fully encapsulates the reinforcement and achieves high structural strength. The freshly cast pallet is then transported to the pallet storage and retrieval machine, which also serves as a curing chamber. Pallets are placed onto heated racks inside the chamber, where temperature and curing conditions are carefully controlled. The heat accelerates hydration, allowing the concrete to reach sufficient strength in a shorter time while maintaining consistent quality. The storage and retrieval system automatically manages the order of pallets to match production flow. A pallet overtaking station allows optimized production sequencing. By rearranging the pallet order, the system ensures that curing times, turning operations, and downstream logistics are perfectly synchronized, maximizing overall plant efficiency. For double wall production, the pallet is transferred to the turning area. Here, the first concrete shell, already hardened to handling strength, is converted into the second shell of the double wall. An overhead pallet turning device lifts and rotates the pallet with the first shell. This turning process places the first shell in the correct orientation, so that it becomes the inner or outer face of the final double wall. The second pallet or mold is then aligned to form the complete double wall configuration, ready for further assembly and final bonding. Once walls and floor slabs are fully cured and assembled, they are transported toward the loading area. Shuttle car systems supply inside loader racks with finished elements, ensuring continuous material flow without bottlenecks. For double walls, a tilting station equipped with an adjustable support beam prepares the panels for vertical handling. The tilting system carefully rotates the wall from horizontal to vertical, while the adjustable beam supports the panel to prevent bending or damage. A mobile lifting platform is used for easy and safe handling of the double walls. Operators can access connection points, attach lifting gear, and guide the elements during lifting and loading. The walls and slabs are then transferred to transport vehicles using the integrated shuttle and loading systems, ready for delivery to the construction site. ASTM A252, GR.2, GR.3 spiral steel pipes are designed specifically for piling applications. Manufactured to international standards such as ASTM, EN, BS, DIN, and GB, these welded steel pipe piles provide high strength, reliable weld quality, and excellent load-bearing performance for foundation and infrastructure projects. Steel plates delivered to the plant are first subjected to incoming inspection. Plates that pass this initial check are transferred into the manufacturing line for further processing. Each plate then undergoes ultrasonic inspection, using multi-channel automated digital ultrasonic flaw detection equipment. This system scans the entire plate to identify potential internal defects such as lamination or slag inclusion. A special double crystal probe is applied to ensure reliable detection of any hidden flaws that could affect product quality. After inspection, the plate edges are trimmed to achieve the required width. Edge milling is then carried out to form the specified groove geometry suitable for longitudinal welding. The prepared plate is fed into the edge gripping and crimping machine, where both sides are bent simultaneously. This operation gives the plate a curvature radius close to that of the finished pipe. Subsequently, the plate enters the forming press, where a 6-cylinder forming machine with a pressure of about 200 kilonewtons shapes it into an open tubular form. Tack welding is applied along the open seam to maintain the pipe shape before final welding. Inside submerged arc welding is then performed on the longitudinal seam. The welding head remains fixed to ensure stable welding parameters, accurate control of weld quality, and continuous recording of welding data. After the inner seam is completed, outside submerged arc welding is carried out along the same longitudinal joint, also with a fixed welding head to ensure consistency and traceability. Before hydrostatic testing, the weld seam is examined using ultrasonic inspection to detect any internal defects along its entire length. This is followed by industrial X-ray television inspection, which produces real-time images of the weld seam to identify possible imperfections. Mechanical expansion is then applied along the full pipe length to straighten, round, and improve dimensional accuracy, while optimizing internal stress distribution. Both pipe ends are cut to length by flame cutting, and the internal and external weld beads at the pipe ends are ground smooth. Hydrostatic testing is performed by sealing both ends and injecting high-pressure water into the pipe to verify its ability to withstand the specified pressure. Test results are automatically recorded and printed. After hydrostatic testing, phased array ultrasonic inspection and additional industrial X-ray inspection are conducted to re-examine the weld and heat-affected zones. Finally, the pipe undergoes finishing operations, including straightening, rounding, end facing, and chamfering. Magnetic particle inspection is used to examine the groove surfaces at both ends. The pipe is then automatically weighed, measured, marked, coded, and recorded in the SCADA and manufacturing execution systems, ensuring full traceability from steel plate to finished pipe. The twin power grinding tool represents a further innovation from Vent, a German manufacturer renowned for high-quality grinding and polishing tools made in Germany. The development of twin power focuses on combining performance, precision, comfort, and above all, safety in professional metalworking applications. Safety is always a top priority at Wendt, and users are reminded to consistently wear appropriate personal protective equipment during operation. The twin power system features an uncomplicated disc mounting solution in the form of an integrated hub, which eliminates the need for a conventional backing pad. This design not only simplifies tool handling, but also reduces setup time and potential mounting errors. Three integrated viewing and cooling windows provide a clear, unobstructed view of the workpiece at all times. This direct visibility allows the operator to work with high precision under all conditions, whether chamfering edges accurately or performing extensive surface grinding. With Twin Power, users maintain full control over the grinding process while benefiting from enhanced comfort and stability. The robust and wear-resistant construction of the Twin Power tool ensures a long service life, even under demanding industrial use. At the same time, it delivers impressive grinding performance with consistent material removal. Increased air circulation around the grinding zone effectively reduces unwanted heat buildup, helping to prevent heat discoloration and protecting the surface quality of the workpiece. Thanks to its thinner yet stronger design, Twin Power offers a high level of safety even in tight or hard-to-reach spaces. By combining durability, efficiency, visibility, and user protection, Twin Power sets a new standard for high-quality grinding and polishing tools without compromising on safety or performance. The rough machining process of a large metal workpiece, a crucial initial stage in heavy industrial manufacturing. In this operation, a long cylindrical steel component is mounted securely on a heavy-duty machining system designed to handle large dimensions and high cutting forces. The main objective of rough machining is to rapidly remove a significant amount of excess material from the raw workpiece in order to achieve a preliminary shape. During the process, a robust cutting tool engages the rotating metal surface with a deep cutting depth and a high feed rate. Large chips are generated and continuously flushed away by a steady flow of coolant, which helps control heat, reduce tool wear, and maintain stable cutting conditions. Precision at this stage is secondary to efficiency, as the focus is on productivity rather than surface finish or tight tolerances. The machine structure provides strong support and rigidity to prevent vibration while machining such heavy components. Operators monitor the process to ensure safe operation and consistent material removal. Once the rough machining stage is completed, the workpiece reaches a near-final geometry, allowing subsequent semi-finishing and finishing operations to achieve the required dimensional accuracy and surface quality. This process is essential in the production of large shafts, pipes, and structural components used in heavy machinery, energy, and industrial applications.